Good day. Today we are going to discuss Module 3 of CE 2121, Measurement of Vertical Distances. So to begin with, we define leveling as the process of directly or indirectly measuring vertical distances to determine elevation of points or their difference in elevation. So next, we define the terms used in leveling. The first term is a level surface, which is a curved surface perpendicular to the direction of gravity or the plumb line at any point. It is best represented by the surface of a large body of still water. So next we have the level line, which is a curved line in a level surface, all points of which are normal to the direction of gravity and is equidistant from the center of the Earth. Next, we have the horizontal surface, which is a plane that is tangent to a level surface at a particular point. It's also perpendicular to the line at the same point. And for a horizontal line, this is a straight line in horizontal plane which is tangent to a level line at one point. So it's perpendicular to the direction of gravity at the point of tangency. So for practical reasons, we assume that a level line and horizontal line are the same for short distances. So next we have your vertical line and your mean sea level. For a vertical line, this is a line parallel to the direction of gravity at any point. So for ordinary purposes, a plumb line held at any point on its surface is always directed toward the center of the sphere or towards the center of the Earth. While for mean sea level, this is an imaginary surface of the sea which is midway between high and low tides. This is taken as the reference surface to which most ground elevations are referred to. So next we have the datum, which is any convenient level surface coincident or parallel with mean sea level. So the elevations of a particular area are usually referred to the datum. So for our references, we use either the mean sea level or the datum. Next, we have your elevation. This is the vertical distance above or below mean sea level or any other selected datum. Next, we have your difference in elevation. This is simply the vertical distance between the two level surfaces in which the points lie. So this is simply computed as the difference of the elevation of one point and a second point, or elevation 1 minus elevation 2. So to understand the terminologies that we just have mentioned, so let's say this is the Earth's surface. So let's have points A and points B to define our measured line. So the curved line now will be a level surface. So this one is our level surface at point B. And this is our level surface or level line at point A. The horizontal plane or the horizontal line is the line tangent to point E, tangent to the level surface at point B, and it will be perpendicular to the line of gravity or your plumb line. So this is our vertical line. So it is towards our center of Earth or center of our sphere. So the horizontal plane and your horizontal line or vertical line will always be perpendicular to each other. So we have your geoid or your mean sea level or any other datum. So this is our reference point. So our elevation now will be from the datum or any reference point to point A is its elevation, and for point B, it will be from the datum or any reference line to point B. And the difference now between elevation E and elevation B will be elevation A minus elevation B. So this is the values that we take in measurement of vertical distances or leveling. So it's either the elevation or the difference in elevation. So we have different methods in determining our vertical distances, and this would include now direct leveling, reciprocal leveling, profile leveling, trigonometric leveling, stadia leveling, barometric leveling, cross-section leveling, and baropit leveling. We will be focusing only for this topic or this module, direct leveling, reciprocal leveling, profile leveling, and trigonometric leveling. So we have the first method, which is direct leveling, or also known as spirit leveling, as we use a spirit level in our measurements. It is the oldest and most employed method of determining elevation of points. The vertical distances are measured above or below a level line to compute for the elevation of points or the difference in elevation. It is used when high degree of accuracy is required. There are different forms of direct leveling, which includes differential leveling, double-rotted leveling, and three-wire leveling. So what we will be focusing under direct leveling is the differential leveling and your three-wire leveling. So we have the first method of direct leveling, which is differential leveling. So this is a technique used to determine differences in elevation between remote points. It requires the use of a surveyor's level together with graduated rods. So again, take note that the elevation is the vertical distance above or below a reference datum. So let's say we have here your ground surface, and we will be measuring 2 points for their vertical distance or their elevations. So the first point will be our benchmark. The second point is our turning point. So any points in between your benchmarks are called the turning point, and the height of the instrument will be measured from the center of your telescope towards your ground or towards the datum. So the reading at the benchmark will be your back sights, and the reading on your turning points will be your foresights, or any reading in front of our direction of leveling is your foresights, and the reading at the back of our direction of leveling is your back sight. So the distance between the point at which you took your back sight and your instrument is your back sight distance, and the distance between your instrument and the point where you took your foresight is your foresight distance. The equations now used for differential leveling is simply elevation plus the back sight is equal to your height of instrument, and the height of instrument minus your foresight is equal to the elevation of the next point. So to further understand our terms, benchmark or BM is a fixed point of reference whose elevation is either known or assumed. The turning point or TP are the intervening point between two benchmarks where the back sights and foresights are taken for continuous reading. And the height of instrument HI is the elevation of line of sight of an instrument above or below a selected reference line. Next, the backside or BS and the foresight or FS. So, backsides are the reading taken on the rod held on a point of known or assumed elevation, and the reading taken on the rod held on a point whose elevation is to be determined are your foresights. The backside distance and the foresight distance are the horizontal distances measured from the center of instrument to the rod on which the backsides and the foresights are taken respectively. So next we have your three-wire leveling, which is a form of off-direct leveling. It is a process of reading and recording rod readings for each of the three horizontal crosshairs on each sighting and averaging the readings for agreement with the center reading. So this is a very accurate method as it gives us immediate results and confirmation. So let's see, we have here your ground. This is our datum or your mean sea level. So we will be reading the elevation of point A. So upon reading, we will have 3 crosshairs reading. So this is the height of your instrument, again from the center to the datum. Your HD is your horizontal distance between the telescope and the point you are taking or reading. So the upper reading is our A, lower reading is B, C is our center reading, and it should be equal to the average of your crosshair readings. So if you're going to look at the telescope of your level, this is what you will see. So you will have your crosshairs. This is our center or middle crosshair. This is the lower, and this is our upper crosshairs. So you will find or see numbers here if you look into your telescopes. So again, A, upper crosshair reading, B is your lower crosshair reading, C is your horizontal or middle crosshair reading, which are all taken at point P. So we have the S, which is a stadia intercept, which is the difference between your upper and lower reading. So S is equal to A minus B. M is the mean of the 3 crosshair readings. So the mean of the crosshair reading should be equal to C. That will be our confirmation. HD again is your horizontal distance. K is the stadia interval factor. And C is your instrument constant. So HI is your height of instrument above or below the datum or mean sea level. Equations for three-wire leveling would include the equation for your stadia intercept, your mean, your horizontal distance, which is equal to the product of the stadia interval and your stadia intercept plus your instrument constant, and the elevation of P is equal to the height of instrument minus the mean value of your readings. So next we have reciprocal leveling, which is the process of leveling where the difference in elevation between 2 points is accurately determined by 2 sets of reciprocal observations. So this is very useful when instruments cannot be set up between 2 points due to obstructions. So example of obstructions will be very large rivers, a cliff, large buildings, and the like. So this is used for long sights to minimize errors of reading, instrument adjustments, and effects of curvature. Next, we have your profile leveling. This is a process of determining elevations of a series of points at a measured interval along a line. So this is usually applied in route surveying and is an extended application of differential leveling. So if this is our route, we will have here your benchmark 1, turning point 1, and benchmark 2. So you will now set up your instrument at any point from your center or from your route. So L, height of instrument. So you will read your back sights and your foresights at equal intervals until you arrive at your last point. So from your readings of back sights and foresights, you will now be able to identify the elevation or the profile of your route or your road. So this is the profile of the road based on. So this is your top view, and this one will be your side view of the route or your road or any horizontal works. So for profile leveling, we also have important terms to know. So we have profile, which is the vertical section of Earth measured along a predetermined or fixed line. We have your stationing, which is a numerical designation given in terms of horizontal distance of any point along a profile line away from your starting point or your benchmark 1. So for stationing, we have two types, your full stations, which are points established along the profile level route at uniformly measured distances. So full stations are measured, for example, at 10, 20, 30, or you can have it at 20, 40, 60, and so on, as long as the station should be of equal distances. The second type of station is your plus stations, which are any intermediate points established along your profile level route which is not designated as a full station. Okay, so for a metric system, we will designate our station as 0 plus 0, 0, 0. So we can have it as 0 plus 0, 10. It means it is 10 meters. So it is the first, or from 0 mark is 10 meters away. So 0 plus 20, it means 20 meters away from your starting point. Then we have 0 plus 0, 0 is your English station. So 0 plus 10 means 10 feet away from your starting point. 1 plus 0, 0 means 100 feet away from the starting point. So if we will have, for example, 0 plus 55, and your full stations are at 10, 20, 30, then 55 is a plus station. So we'll have examples later on to further understand the difference between full and plus stations. So next we have your intermediate foresights. So the intermediate foresights, or also known as ground rod readings, are taken along the center line of proposed project to provide an accurate representation of your ground surface. So we will also have your backsights and foresights in profile leveling. So we have your profile paper, which is a special heavy grade graphing paper used for plotting profiles. Next, we have your trigonometric leveling, or this is also our indirect leveling. So it is the determination of differences in elevations between 2 points based on measurements of vertical angles or a zenith and either of the horizontal or slope distance between points. So it employs trigonometric computations after measuring your distances and angles. Thus, the name trigonometric leveling. So, its required distance is usually obtained by stadia, triangulation, or direct taping. So, the vertical angles or the zeniths may be angles of elevation or plus angles or angles of depression, meaning the angle is measured below your horizontal. So, trigonometric leveling is extensively used when undertaking topographic surveys over rugged or rolling terrain. So, it provides rapid means of determining distances and elevation of points. So, let's say we have here points A and B, at which point A is the location of your instrument and point B is the location of your leveling rod. So, from here, we are able to get your horizontal distance D and your slope distance S. So with this, we will be able to compute for your vertical distance between the height of instrument and your point B. So vertical distance V can be computed as D tangent of alpha or V equal to sine alpha times S. So also, we will be able to get your height of instruments, which is measured from the center of the scope to your point A. And then we will have your rod reading. So it's the measurement from point B to the line of sight of the rod. And then we will have your difference in elevation between A and B. So the difference in elevation between points A and B can now be computed as D tangent alpha, or that's the vertical, plus your height of instrument minus your rod reading. Or it can also be computed as S sine of alpha plus HI minus rod reading. And again, from your datum or mean sea level, we will have your elevation A and your elevation B, at which elevation B now is equal to elevation A plus the difference in elevation of AB. So this is applied if we know the elevation of A. So this method is simply applied if our lengths are measured until 300 meters. So if our measurements exceed 300 meters, we are now going to apply our effects of curvature and refraction. So for longer horizontal distances, an electronic distance measuring instrument and precise optical theodolites are utilized in measuring your slope distances. So the corrections for combined effects of curvature and refraction is added to our computation. So the Earth's curvature or the curvature effect is the amount by which the level surface passing through point A departs from the horizontal plane at distance AP from any point of tangency. Or this is simply the vertical distance between your horizontal line and your level line. So let's say we have here point A, which is the location of the instrument. Point P is the location of your rod at which you are going to measure the elevation. So your horizontal distance is AB, which is parallel to the horizontal line tangent at point A. So this is our level line, AC. So the difference now between your horizontal and your level line is our curvature effect or our error due to curvature of Earth. So C will be our true reading of point P, and B is your observed reading of point P. So we will have K, which is the length of line of sight of AB, which is measured in km. BC, or B minus C, is the effect of curvature HC, which is equivalent to 0.0785 K squared. And then next, we have the refraction effect. So as we know, rays of light would be bent because of refraction. So the rays formed or from the rod to the instrument will follow a curved or concave path AD towards the Earth, as upper layers of air are denser than those that are near your Earth. So we will have your level line C, and because of refraction, what we will be reading later on is at D. So with this, our HR now is the difference between your horizontal and your refracted reading. So BD is your effect of refraction. D is the rod reading at point P. So your effect of refraction is 1/7 of the curvature, or it's 14% of the curvature. So this is equivalent now to 0.0112 of K squared. So if we're going to apply now the two effects, curvature and refraction, so we have here your horizontal line at which you take point D. This is the arc caused by the refraction of our reading, point D, and this is the true reading of the rod, so at level line. So HR is B, or difference between B and D. HC is the difference between B and C. So for the combined effects of refraction and curvature, so the curvature would increase our staff reading, and the reaction would decrease our reading. So as you can see, curvature is greater than the refraction. Thus, we can now compute for our difference in elevation. So this is V plus HI minus RR. So if we have the effects of curvature and refraction, we have to add our combined effects. This is applicable if our reading is an elevation reading or above the horizontal. Our computation for the difference in elevation will vary if it will be a depression angle. So we'll have an example later. So combined error effect of curvature of refraction, HCR now is equal to CD. So this is our HCR, which is equal now to HC minus HR, which will give us now the value of 0.675 K squared. So again, the value of K should be in kilometers, but the resulting value of HCR is in meters. So this one is in kilometers, the result is in meters. Okay, so let's solve some problems of leveling. So let's have example 1. Determine the elevation of BM2 from the following figure. Tabulate your answers and apply arithmetic check for back sides and for sides. So from this problem, we have now benchmark 1 and benchmark 2. So in order to determine the elevation of benchmark 2, we will have to assign turning points. So you can assign 1 turning point or 2 or more than 2. So from TP, so between benchmark and your turning point, you will place your instrument, and the reading taken at the back of the instrument is our backside. And the reading in front of the instrument is our foresight. So at TP2, between TP1 and TP2, backside is 6, foresight is 3.15. So for this reading, this is our backside, this is our foresight. So for our solution, for our table, we'll have your station, your backside reading, your height of instrument, your foresight, your elevation. So our stations are your benchmark 1, TP1, TP2, and benchmark 2. So for backside of benchmark 1, that is 1.4. Next, we have benchmark of TP1 is 6.0. Benchmark of TP2 is 5.2. We do not have a benchmark at BM2, or we do not have a backside for BM2. So next, we have your foresights. So we do not have a foresight at BM1. Foresight of TP1 is 3.23. Foresight of TP2, 3.15. Foresight of BM2 is 2.19. So once we have established the backsides and foresights for each station, we now compute for your height of instrument and your elevation. So for the height of instrument, that is equivalent to the elevation of the station plus its backside. So for BM1, we know its elevation, so it will be 50 plus 1.4, so it will give us 51.4. So next, we'll have the elevation of the next point, which is TP1. So it will be height of instrument 51.40 minus 3.23 is equal to 48.17. HI is elevation plus backside. So it is 54.17. Elevation is height of instrument minus foresight, 51.02. Height of instrument is elevation plus backside is 56.22. And lastly, elevation is height of instrument minus foresight, and that is 54.03. So therefore, the elevation of benchmark 2 is equal to 54.03 meters. So for our checking, we add up our backsides, 12.6, our foresights, 8.57. So for checking, we determine the difference of your backsides and foresights and the difference in elevation. So the difference in your backsides and foresights is 4.03. Difference in elevation of benchmark 1 and benchmark 2 is also 4.3. So therefore, it is okay. So next problem, for the given figure, we determine now the elevation of benchmark 2 and we apply your arithmetic check for our answer. So again, we'll have our field notes in this orientation. Station, backside, height of instrument, foresight, and elevation. So for our stations, we have your benchmark 1, TP1, TP2, TP3, and your benchmark 2. So backside for benchmark 1 is 2.19. Backside of TP2 is 5.20. Backside of TP2 is 1.14. Backside of TP3 is 1.17. BM1 we do not have BM2 we do not have a backside. For our foresights, we have for benchmark 1, wala tayong foresight. For TP1, so we have your foresight. Foresight of TP2, 4.18. Foresight of TP3, 2.25. And foresight of benchmark 2 is 1.23. So we are given the elevation of benchmark 1, 427.18. So again, our equation, HI is equal to elevation plus plus backside. Elevation equal to HI minus FS. So let's solve. So elevation plus backside equal to HI 429.37. HI minus FS 425.1. Elevation plus backside 430.31. Height of instrument minus foresight 426.13. Elevation plus backside 427.27. Height of instrument minus foresight 425.02. Elevation plus backside 426.19. And height of instrument minus foresight is 424.96. So from the problem, our elevation for benchmark 2 is 424.96. So for our checking, compute for the sum of your backsides and foresights. So 9.71 and 11.93. And then we could, another way to check, elevation of the first point plus the sum of the backsides is 436.89. And then check elevation of the second point plus the foresights is equal to 436.89. So again, they are the same. So therefore, we have an okay arithmetic solution. So next, we have your three-wire leveling. So an engineer's level with stadia constant of 0.30 meters was set up to the line between points A and B. The following crosshair readings were observed. Determine the length of line AB if the stadia interval factor of the level is 100. So from this, we have now A, B, C for rod A, and we have A, B, C for rod B. So for our solution, horizontal distance is KS plus C, S will be our upper minus lower crosshair readings. So for our table, we'll have your rod position, upper reading, middle, lower reading, stadia intercept S, the mean M, and our horizontal distance HD. So for our rod positions, we have AB, BC. And then we have 1.333 for the upper reading of A. Middle reading is 1.175. Lower reading is 1.02. And then for B, we'll have 1.977, 1.854, and 1.736. So for stadia intercept, upper minus lower will give us 0.310 for A and 0.236 for B. For the mean, it's 1.75, which is the same as our middle reading. And for B, 1.854, same with our middle reading. So meaning, we have a correct readings for our survey. So for our horizontal distance, it's simply K 100 times S plus 0.3. So we have horizontal distance of A2, the instrument is 31.3, and the horizontal distance of point B2, the instrument is 23.9. So therefore, our HD total or the distance between A and B is 55.2 meters. Okay. So next example, we have the following data taken from a three-wire leveling survey. So let us determine the distance between BM1 and BM2. Use the stadia interval 100 and instrument constant of 0.45 for your computations. So for our solution, let us define our equations. HD, horizontal distance, is equal to KS plus C. S is equal to the upper minus lower reading. Our given for K is 100 and for our constant is 0.45. So we will have first your BM1 to TP1 line, which is taken, or the readings will be taken from points BM1 and TP1. Then we have the next line, 2 is taken from TP1 and BM2. So for our stadia intercept, our values now are 1.964 for BM1, TP1, stadia intercept for line 1 is 3.048. Stadia intercept of TP2 or TP1 at line 2 is 1.984, and for BM2, line 2 is 2.104. So for our mean values, let us check if we have the correct readings. So the mean value for BM1 is 3.204. So it's the same. Next, TP1, line 1, 3.722. Same. Next, 3.286. Same for TP1, line 2. And 2.175. Same for BM2, line 2. So for our horizontal distance, HD, for BM1, line 1, it will now be equivalent to 196.85. HD of TP1 to instrument is 305.25. And then we have for TP1 to instrument for line 2 is 198.85. And instrument to BM2 is 210.85. So adding up the lines or the distances for BM1 to TP1 will have 502.10, and for the distance between TP1 and BM2 we have 409.70. So therefore the total length now for BM1 to BM2 is 911.80 meters. Have example 5. Determine the profile of the road section given and the elevation of BM2 and draw a profile of the section. So for our road section, we establish BM1 and BM2 at the center. So we also establish a turning point at which we get our readings. So we'll have our stations at 10 feet interval. For our instrument, we place it at any convenient distance from our center line. So with this, we take our backside readings at BM1. And for all our stations, this will be our foresight readings. If you are not able to get any more foresight readings, we may transfer our instruments at a different location and we will get another value for our backside reading. And this will be the backside at your turning point. And again, at all other stations will be our foresights until we arrive at your BM2 or your last point. So please take note of our station 0 plus 53.35 as this is an example of a plus station which is not equal or is not in interval with the given full stations. So any distance or any stations in between our full stations are considered as our plus stations. So for our solution, we have our field notes containing the point, station, backside, height of instrument, intermediate foresight, elevation, and the rise or fall of our points. So from our given, our points are BM1, TP1, and BM2. So from point BM1, we take our readings at station 0 plus 00, 0 plus 10, 0 plus 20, 0 plus 30. And at TP1, we take our readings at 0 plus 40, 0 plus 50, 0 plus 53.35, plus 0, 0 plus 60, 0 plus 70, 0 plus 80, 0 plus 90, and at BM2 is at station 1 plus 00. So from our given values, our measured values, we now compute for our height of instrument, elevation plus backside is 108.620. So height minus or HI, height of instrument, minus your foresight. For our full stations, we subtract the intermediate foresight. So that will be 620 minus 2.285. So that will give us an elevation of 106.330. For station 0 plus 10, it will be 108.620 minus 1 plus 560. Next, we have station 0 plus 20. So HI plus FIFS. Elevation of 0 plus 30 is HI plus IFS. And this elevation of TP1 is HI plus the foresight. And then for our height of instrument, for TP1, it will now be elevation plus backside, 108.390. And for the elevation of our foresights taken at height of instrument 2, we will add or we will subtract the intermediate foresights and foresights from your HI. So for 0 plus 50, elevation is 104.5 0.925, station 53.35, 104.435, station 0 plus 60, 105.27, station 0 plus 70 is 105.375, station 0 plus 80 is 105.81, station 0 plus 90 is 106.435, and lastly, the elevation of BM2 is now computed as 106.925. So remember, for profile leveling, we only take our height of instrument at our station or our point. No need to compute for the height of instrument for each station. So for the rise or fall of our points or our stations, this is simply subtracting our backside and your height of instrument, or the height of instrument and the intermediate foresights and foresight. So for every level. So for station 0 plus 0, 0, subtract 3005 to hours na ako nagre-record dito. Ba? Okay, so for the rise and fall, we subtract the values of the backsides and your foresights for every level. So for station 0 plus 0, 0, that will be backside minus the foresight, giving us a positive 720, meaning there is a rise in elevation. So next, difference of your foresights. So 725. So at station 0 plus 10, it means there is again a rise in the station. Negative 0.225. So this is now a fall. So meaning we went down in elevation. So negative 320. So next, we subtract 2.105 and 3.105. So that's negative 101. Then next, we have 3.465 minus 3105. So negative 590. So next, so subtract for every station the values of foresights. So if there is no foresight to be subtracted from, you start it with the backside. So it simply means that from our starting position, there was a rise, and then a fall, and rise again. So for our summation of backsides and foresights, you can check again for our arithmetic solution. So you simply take the difference of backside and foresight and the difference in the first and last elevations. So they should be equivalent. So for our profile, from our computed elevations, we can now graph our section. So for the x-axis, this will be for our station, horizontal distances. And for our y-axis, this will be our elevations. So from the data, we will now see that the elevation of our section is a rise, a fall, and a rise. So next problem, example number 6. So from the given data obtained from profile leveling, compute the elevation for each station. The difference in elevation between station 0 plus 040 and station 0 plus 180. Draw a graph of the profile. So from this given, we now solve for our elevations by computing for our HI. So elevation plus backside, 201.285. Elevation now is HI minus IFS for 0 plus 020 until 0 plus 100. So that will be 198.94, 199.984. We have 198.905, 199.496, and 198.829. For TP1, the elevation will be HI minus FS, so 200.521. So we have a backside, so elevation plus backside will be your HI, which is 202.835. So for the elevations of 0 plus 120 to 0 plus 180, we will now have 202.835 minus the intermediate 4 sides. So for 0 plus 120, we will have 201.938. For 0 plus 140, 199.848. 0 plus 160 is 200.521. 0 plus 180 will have an elevation of 201.273. And for TP2, its elevation will be 202.835 minus 2.721, giving us 200.114. And for our HI, or height of instrument, elevation plus backside, it will be 199.867. And for our elevation from TP2 to 0 plus 240, we will have for 0 plus 200, 200.084. Station 0 plus 220 is 198.334. And 0 plus 240 is 198.665. So these are the elevations for each of our stations. And for the difference in elevation of station 0 plus 040 and 0 plus 180, we simply subtract the elevations of the two. So that is now 201.273 minus 199.984. So the difference in elevation of 0 plus 040 and 0 plus 180 is 1.289 meters. For our profile section, again from our computed elevations, so we have here our stations at the horizontal, elevation at the vertical. So our section now looks like this one. So you are traveling up and down in this route. So next example, number 7, trigonometric leveling. A vertical angle of negative 12 degree, 25 minutes is measured to the top of a water tank from an instrument set up on a hill 585 meters away from it. The telescope of the instrument is 1.45 meters above the ground, whose elevation is 462.73 meters. Making due allowance for the Earth's curvature and atmospheric refraction, determine the elevation of the base of water tank if the tank is 32 meters high. So to solve this problem, let's have a simple diagram. So we have the elevation of our point P is 462.73. So this should be the So the elevation is this one till this point. So we have the height of our tank is 32 meters. Distance is 585 between the instrument and point B. So we have a negative angle, meaning the angle is below the horizontal. So we have the instrument higher compared to the point observed. So for this problem, we have to solve for our difference in elevation and the elevation of point B. So before we solve for the elevation of point B, we have to solve first for the value of V. And for V, we can compute this using the relationship of tangent phi or tangent alpha based on the triangle vertical over the horizontal distance. Our vertical distance now is equal to d tangent phi, giving us 585 tangent 12 degree 25 minutes, giving us a value of 128.8. So next, we solve for... So since our distance or horizontal distance is greater than 300 meters, we'll now be applying the curvature and refraction effects of Earth. So with this, we now apply HCR, or the combined effects of curvature and refraction, equal to 0.675 K squared. So K is our distance between the point P and point B. So since K should be in meters or in kilometers, so we convert this by dividing it to 1,000. So HCR now will be equivalent to 0.023 meters. So to solve for point B, or the elevation of point B, we have to determine first the difference of elevation of point P and point B. And this is computed as the height of the tank plus V minus your HI. And then we subtract your curvature and refraction. So substituting our values, we will arrive at the difference in elevation of point B and P as 159.33 meters. So once we have solved for this, we can now solve for the elevation of point B as elevation of P minus the difference in elevation. We will now arrive at the elevation of B equal to 303.4 meters. So thank you for listening. Practice solving the problems in the module on vertical measurements. The activities for the evaluate portion will be posted in the classroom. So for your reference, you can use this to check the topic.